Hello and welcome to this new video where we'll talk about resistors. The objectives that will be covered in the video are: firstly, stating Ohm's law relative to a resistor, measuring the resistance of a resistor, and finally, how to find the equivalent resistance value for different circuit types along with formula derivation and applications. A resistor has an important role to play in the majority of electrical circuits. As you can see in the figure, an electric circuit is formed when a conductive path is created to allow electric charges to continuously flow. This continuous displacement of electric charge through the conductors of a circuit is called a current, and it's often referred to in terms of flow, just like the flow of a liquid through a pipe. In other words, electric currents tend to move through the conductors with some degree of opposition. This opposition is more adequately referred to as resistance, and the amount of current flow across a circuit therefore depends on the amount of voltage and resistance in the circuit. Now, the force driving charges to flow in a circuit is the voltage. Voltage is a measure of potential energy difference between two specific points in the circuit. To conclude, a resistor is a passive component with the main job of providing resistance in a circuit, hence the name resistor, and its main function is to limit current flow. Ohm's law states the relationship between electric current and the voltage. In 1827, George Simon Ohm, a German physicist, was the first to experimentally verify Ohm's law, subsequently the name, and published his findings in a paper that same year. Ohm's principal discovery was that the amount of electric current through a metal conductor in a circuit is directly proportional to the voltage across it. Ohm expressed his discovery in the form of a simple equation describing how voltage, current, and resistance correlate. After conducting numerous experiments and documenting results, he deduced what we know now as Ohm's law relative to a resistor, U is equal to R times I. In this algebraic expression, the voltage U is equal to the current I multiplied by the resistance R. We can further manipulate this equation into two variations, solving for I and for R respectively. I is equal to U over R, and R is equal to U over I. In all three formats of the equation, remember to use SI units. In other words, U should be in volts, R in ohms, and I in amperes. The IV characteristic curves, short for current voltage characteristic curves, show the relationship between the current flowing through an electronic device and the applied voltage across its terminals. The previously described formula for Ohm's law allows us to deduce the IV curve relevant to a resistor. As the law clearly shows, for a resistor with resistance R, the voltage across it, U, is directly proportional to the current I passing through the resistor. More importantly, the formula shows that the IV measurement points for a specific resistor move on a straight line passing through the origin and having a slope equal to R. This can be clearly noticed when comparing the Ohm's law formula with the equation of a straight line passing through the origin, y is equal to A times x. Finally, the IV curve for a resistor is displayed in this figure, and as Ohm's law would indicate, the IV curve is a straight line with slope R as just explained, assuming that voltage is plotted on the vertical axis and the current on the horizontal axis. As stated earlier, a resistor basically limits the flow of charge in a circuit. Most circuits, however, have more than one resistor. If several resistors are connected together, the current supplied by the source in the circuit will be opposed or partially inhibited by the resultant of those resistors. Thus, the importance of being able to find the equivalent resistance of several resistors in a circuit. The equivalent resistance of a combination of resistors depends on both their individual values and how they are connected. The simplest combinations of resistors are series and parallel connections. Let's start with the series connectivity case. In a series circuit, the output current of the first resistor flows into the input of the second resistor, so on and so forth. Therefore, the current is the same in all series resistors. In other terms, resistors are said to be in series whenever the current flows through the resistor sequentially. Consider now this figure showing three resistors in series with an applied voltage UAD. Let's start by applying the law of addition of voltages in this series circuit. We can write UAD is equal to UAB plus UBC plus UCD. This equation can be written as follows: U total is equal to UR1 plus UR2 plus UR3, as we have the resistance R1 between A and B, R2 between B and C, and R3 between C and D. By applying Ohm's law for a resistor, we can therefore replace U with R times I. Therefore, R total times I is equal to R1 I1 plus R2 I2 plus R3 I3. Since there is only one path for the charges to follow, the current is the same through every resistor, as per the law of uniqueness of current in series circuit. The equality can thus be simplified to an equivalent resistance, R total, being simply equal to the sum of the resistances of the individual resistors. Thus, R total is equal to R1 plus R2 plus R3. Keep in mind that the formula we just derived holds for any number of resistors connected in series. We just add their values to get the total resistance. It's also important to note that in series circuits, R equivalent is greater than all the individual resistance values, as it is obtained by summing the values up. Moving to parallel connections. In this figure, the resistors are in a parallel configuration. A quick reminder about parallel connections: circuit elements connected in parallel have both ends connected to one another, as if two people were holding their left hands together and their right hands together. In this case, and as per the law of addition of currents in parallel, the sum of the individual currents in each parallel branch is equal to the main current that flows into the parallel connections. Therefore, I total is equal to I1 plus I2 plus I3. As per Ohm's law, I for resistors is nothing but U over R. Hence, we can say that U over R equivalent or R total is equal to U1 over R1 plus U2 over R2 plus U3 over R3. Now, using the law of uniqueness of voltage in parallel connections, we know that the voltage is the same across each of the parallel connected resistors. In other words, U1 is equal to U2 is equal to U3 and is equal to U total. The previous equation can thus be simplified to 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. Again, the equation we just derived can be generalized and applied to any number of resistors connected in parallel. The inverse of R equivalent would be equal to the sum of inverses of all individual resistances connected in parallel. Simple mathematical analysis can also tell us that the equivalent resistance obtained from the just explained equation is in fact smaller than even the smallest of the parallel connected resistors. Well, that's all for this video. I'll be posting soon other videos where we shall discuss further applications on equivalent resistance, focusing more on complex series and parallel resistor arrangements.